Hi everybody, Jonathan here. This video is about my take on section 6.1, which is about the areas between curves. But that's actually slightly dishonest. This video is more going to be like how we use the power of calculus in order to solve problems by coming up with good approximations. Now, of all the formulas you're going to be learning in Calc 2, the formula for the area between curves is one of the simpler ones. Basically, if you want to find the area between the curves y equals f of x and y equals g of x, where f of x is bigger than or equal to g of x, all you have to do is take the integral from a to b of f of x minus g of x. Now, there are several ways in which this simple formula can be made more complicated. For example, sometimes you might have x defined as a function of y, and you want to find the area between two curves x equals f of y and x equals g of y. Well, the formula is exactly the same then, except now it's just the integral of f minus g, but now you're integrating with respect to y. And the final wrinkle that you have to deal with in this section is that sometimes you want to find the area between curves where one function isn't necessarily bigger than the other function. Over some regions, f might be bigger, and over other functions, g might be bigger. Well, us mathematicians, we love to have simple formulas. So in that case, we have the simple looking formula, a is the integral from a to b of the absolute value of f of x minus g of x dx. However, integrating absolute values is very hard to do directly, so if you ever have to solve a problem like that, what you have to do is split the region up into two areas. One area where one function is bigger and the other area where the other function is bigger. And then you just split up the integral over two integrals where you just split up the point where over point or points where one function becomes bigger than the other. So here the cosine was bigger between 0 and pi over 4, whereas sine is bigger between pi over 4 and pi over 2. So over this region, sine, you do sine x minus cosine x, and over the first region, you do cosine x minus sine x. Now for the rest of this video, I would like to explain to you where formulas like the formula for the area between two curves comes from. It comes from the power of calculus, which allows you to take a system of approximations to a problem and turn it into an exact answer by taking a limit. So back when you first learned about the integral, the actual definition of an integral is basically this thing here, which says that the integral from a to b of f of x is equal to the limit as n goes to infinity of f of x1 delta x plus f of f2 times delta x and so on, all the way up to f of xn times delta x, where the interval ab is divided into n equal subintervals, each of with delta x, and x1 and x2 and all that are any point in the ith subinterval. So that's quite a mouthful to say. And why did things get defined this way? Well, it all came about from trying to solve this area problem. In the area problem, you're trying to find the area enclosed by several curves. And here, we're trying to find the area enclosed by the curve y equals sine x plus 1, and the vertical lines x equals 0, and the vertical lines x equals pi, and the x-axis. And the way we find that area is first we come up with an approximation. We divide the area up into a bunch of rectangles. And right now, I've made this slider that can adjust the number of rectangles we're going to use to approximate the area with. It goes all the way down to 1, so that's our approximation when there's only one rectangle, and there it is with 2, and with 3, and well, with 4, and with 5, and with 8, and so on and so on and so on. And you can see we get a better, as you make the number of rectangles really large, then the area of all the rectangles combines to be almost exactly the actual area we care about. So making the number of rectangles small again, each rectangle we know the area for because the area of a rectangle is the width times the height. The width of each rectangle is delta x, so that's why we say this first rectangle has area f of x1 delta x, because the height is going to be the height at the right endpoint. What we do is we use the function f of x1 because that's the distance from the x-axis up to the curve. We use that for the height of the rectangle, and delta x is the width. And we do that for all the rectangles, and therefore we get this nice approximation of the area. And by letting the limit as n goes to infinity of that approximation, we get an exact answer. And this is a typical mathematics mumbo-jumbo, where you have a formula that's exactly correct, except for all but the simplest of functions, this limit is going to be impossible to find directly. No matter how good you are at taking limits, it's a limit of a sum that keeps getting bigger and bigger, and that's really hard to find. However, what saves us is the fundamental theorem of calculus. The fundamental theorem of calculus says whenever you have a limit of sums like this, which we define to be the definite integral, you can actually find that limit by taking antiderivatives. So here capital F is the antiderivative of little f, and then doing capital F of b minus capital F of a. And finding antiderivatives, while it's not necessarily easy, it's way easier than finding this limit of this expanding sum. Now, this idea of taking the limit of a bunch of approximations and turning it into an exact answer can be used on way more types of problems than just finding areas. For example, we can use it to try and find the length of a curve. Right now, we've got this lovely looking spiral. It's very aesthetically pleasing. And if we want to find the length of the spiral, what we can do is we can try to approximate the spiral with a bunch of straight lines, because we know how to find the length of a line segment using the Pythagorean theorem. So what we're going to do is we're going to just make a bunch of points on the line, and I can control the number of points here. So there I've got a bunch of number of points on the curve, I should say. And then I make a segment, I make a straight line segment between the points. And right now, when I've got 7 such segments, the approximation is not very good. But you can still calculate the length of each of these line segments to get a halfway decent approximation. And by increasing the number of line segments, you can now see that the line segments are getting to be a better approximation for the curve, for the length of the curve. And I increase the number of line segments further, and at this point you can barely tell the line segments apart from the curve. And then by increasing it, at this point you can't tell that the line segments are different from the curve at all, and we get that the length is about 20.16. Well, there goes to 20.17 as we increase it even more. If I show the points again, we've just got a whole bunch of points crammed along the curve, and we're finding the length of the line segment between all those points. So we'll see later that this is just an approximation, but by taking the limit as the number of segments goes to infinity, we can turn that into another integral, which we can then find using the fundamental theorem of calculus. Now, the formula for the area between curves came from this method of taking a limit of approximations. You divide the area up into a bunch of rectangles, each of which delta x. Then the height of each rectangle is going to be the distance between the y values, so it's going to be f of xi star minus g of xi star, where xi star is just any point in the ith subinterval. And by taking the limit of the sum of those areas, we get an exact answer. And then the fundamental theorem of calculus kicks in, and we turn it into an integral, which we find by antiderivatives.